So today, first of all, thank you for organizing this meetup. Lots of interesting presentations already, and hopefully mine would also be of some relevance to the audience. It's gonna cover a slightly different topic. So I'm mostly gonna focus on the recent paper that we presented at ICRA on object 6D pose estimation and tracking, especially in indoor cluttered scenes. But before going there, I want to talk about some of the broader scope of work that we are doing in my research group at the University of Washington in Seattle. So we are, or one of our big research thrust areas is on robust and generalizable robot perception for autonomous mobile robots, specifically mostly looking at indoor robots. And we are mostly motivated by the problems of how to make these robots be deployable in indoor settings, could be like homes, public spaces for long-term autonomous operations. And there we, of course, know that it's the scenes are gonna change, new objects are gonna show up, and the robot has to figure out what those objects are, how they can be manipulated for and other downstream applications like those. So we believe for at least these kinds of long-term autonomy and deployment type problems, like we really need methods which can leverage like the structure of the environment, which could come from like the shape of the objects or the dynamics of the environment, and like it's gonna be very challenging for pure end-to-end like visual learning methods to work exhaustively in these kinds of scenarios with the types of shifts that we expect in the test time, particularly. So, in with respect to that, we started first working on a kind of robust object detection and recognition, and that's not the focus of my talk here. But I'm just gonna quickly summarize the work that we have done over the past couple of years, and we published a couple of papers. You can see the links here, including the code and the data set also that we generated. So our idea here is that we want to have like very kind of frugal or minimal sort of training that can be done entirely on synthetic images. So it's not going to rely on any real world data for training, or at least not as much as possible. So we assume so far that we do have like CAD models or mesh files for the objects. Right now, we are working on some new techniques that can potentially remove that restriction. But so far, what the results that we have, I do assume that we have these CAD models or mesh files. And then we like synthesize lots of images or views of these objects, and then essentially rely on some very interesting topological descriptors to like come up with like 3D shape and also color based or appearance based features that can capture the realization of these objects at a higher level of granularity than what we can typically specify otherwise in the end-to-end sort of learning models. So there is a lot of technical details on how we do that, and I don't think I have the time today to get into that, but I do encourage you to check out the details of how we manage to execute it. Again, emphasizing that we do not use any real world data for training these descriptors, and then once the features are generated, you can feed them to very like simple classical classifiers, like a very simple neural network or even like an SVM, and you can still do the recognition in a robust manner. So here is like a quick demonstration on the low-cost robot hardware, and you can see it's in an like a fairly cluttered indoor scene with low lighting conditions. We try to kind of mimic some kind of warehouse type scenes, and we compare our approach, this topology-inspired approach, with like a vision transformer model. And in fact, we give some extra benefit to the vision transformer model. It does have access to some real world data. It has been fine tuned on both synthetic and real world data. And we are dealing only with synthetic data for our model, and it still performs a lot more accurately and generalizes much better to unseen scenes. And we see like the benefits actually increasing when we get to more and more of these highly occluded or cluttered scenarios. So that was pretty interesting to us. So that kind of led us to start thinking about, okay, this is just like a recognition which can help with semantic mapping and other things. But ultimately, when we want the robots to start manipulating objects, we need to also be able to like perceive the 60 pose and track those poses of the objects robustly in real time. Of course, there has been a lot of ongoing work in this field in broadly in computer vision, and we started using some of those like even pretty recent ones like foundation pose and all. And we realized that while they are like fairly accurate, they are not very suitable or yet at least for real-time applications where we want to do complete onboard processing on robots, and which means we have to make them work on edge devices, which can be GPU processors, but it has to be edge devices, so it's not any centralized computation. And we want it to run alongside full autonomy stack of the robot, which means it has to do everything else, including navigation, mapping, and then manipulation planning, motion planning, all of it. So perception cannot like consume the entire processing resources. So we wanted something which is at least comparable in terms of accuracy, would generalize well to unseen objects, and most importantly for us for this work at least was to make sure it's lightweight enough that it can run in real time at least like 5 frames per second or more speed on a robot. So those were like our specific goals as we started thinking about how can we again exploit some structure in the objects that the robots is viewing to be able to do their pose estimation and tracking. So the key idea there we came up with is this notion of color pairs. So we're not talking about again individual colors, but color pair, and it's kind of visualized it here. Individually, we know like the colors change quite a lot depending on your ambient lighting conditions. But if we, assuming we have fairly rich texture or color information on the objects, we have many kinds of colors, and we can look at those in a pairwise manner, or maybe in the future as more of n tuples, and try to identify some associations or correspondences among these pairs of colors, which would be a lot more robust to like the background lighting conditions. So one of the things that we did was to convert everything to the Scilab color space rather than maybe the RGB or the HSV. So that makes it more the representation of the color in terms of chrome and luminosity a lot more robust. So we did that, and then we created these kinds of triangles with these colors nodes as the vertices of the triangles, and came up with a bunch of different sort of handcrafted features to characterize like the geometry of these color pair triangles that we constructed. And we can find more details in our paper. So things that we considered would be like the relative contrast, their relative luminosity, as well as their directional alignments. And then the idea was that using these color pairs, we can have sort of a unified framework which can do both pose estimation. That means this kind of a zero shot thing, like the robot first views the scene and it estimates the poses of all the objects. And then as it moves around in the scene, it can still kind of robustly keep tracking the pose. So we use the same sort of unified features of color pairs to do both pose estimation and tracking, and again in real time. We do use neural networks internally for some of the processes, but as you can see here, it's not reliant on very heavyweight architectures with pre-trained encoders. So this is kind of the overall pipeline. Again, one of the similarities here with what I was explaining earlier for object recognition is that all the sort of offline like training slash kind of model preparation processing is done purely based on like synthetic images. This is again not using any kind of real world data in that phase, the offline phase at all. But it again has the same sort of restriction as earlier, that we assume that we know the overall object categories and we have access to like the mesh files or CAD models of these objects. So we again render these objects from a bunch of different views. You will see that more in a subsequent slide. And for all of these different views, for all of these objects, we do this color pair extraction using those triangle-based features that I talked about. And then online, you can see that there are two kind of branches. So one side, we have the branch for the zero shot pose estimation, and then we have on the right hand side of the figure a branch for the optical flow based pose tracking. So the common part for both these branches that are happening online is that from the depth camera images, we like get the actual like image, segmented image. So we do have to do like object segmentation. So we get segmented the map of or mask of the object from the depth camera in real time. And then from there, we have a very similar color pair extraction scheme as we do for the offline rendered views. And then we do this kind of classical matching and comparison, but now at the color pair level using again some specialized technique that I'm going to talk about a little bit more in detail, which generates some corresponding like point clouds. You have some reference point clouds from your offline library. You have the query point cloud, and then the rest of it is almost the universal ICP method, which is slightly customized. We do some initial pose voting based on, again, the color matches. So that's what is happening on the pose estimation side of things. On pose tracking side of things, we use, again, the classical optical flow method, but try to make it more robust because anyone who has worked with optical flow knows that if there are some kind of jerky motions or some like maybe missing frames, then the method tends to lose its accuracy quite easily. So we kind of boost the optical flow based tracking method with our color pair based filtering to make it more robust. And we in fact do some tests where we artificially do not feed certain frames, consecutive set of frames to the method. We skip a bunch of frames and then we give a frame after a while, and then our method is still able to sort of in a continuous sense be able to track the object's poses in real time. So that's the overall goal. So a little bit more details about the individual steps of the pipeline. So they are fairly simple and intuitive, nothing too fancy going on here. So for view generation, it's again a simple idea. It's all synthetic rendered image. So we choose like 14 views to get a decent coverage from different viewpoints. For the color extraction, before we can construct the color pairs and all those triangles and all, we have to extract the colors themselves. So that's based on a combination of like the gradient along the two axes and their magnitudes. The surface point classification is again pretty straightforward. Uh, and then one of the other things before we run the ICP method I was talking about is this initial pose voting. So there we again leverage all these color pairs that we have already extracted and the triangles that I spoke about, and look at those triangles from a slightly different perspective with some more semantic labels associated to it, and do some comparison of these semantic color triangles before we feed them to the ICP method. So that helps with getting good initial poses as the seed points to the ICP method. Again, for anyone who has worked with ICP would know like the quality of the results or how quickly converges depends a lot on your quality of the initial pose guesses, and looking at these relative or weights of the probable poses as the initial seed points using color pair information helps a lot with the performance. Okay, so this is more of that. And then this is kind of an illustration of how we use these color pair based point clouds also to boost our optical flow method. To essentially, you can think about it as kind of an outlier filtering or noise removal type scheme that's added on top of optical flow. So with that, finally, the last step in order to do the post tracking is our version of the PNP algorithm. So there we do use DGCNN, graph convolutional neural network, attention with an attention head. So that is, I would say, within our overall pipeline, the most kind of computationally expensive step, but since this is the only time we are using it, and we are using like a fairly small set of kind of handcrafted features, it works efficiently, and in fact it works quite fast in real time, as you would see in some of the results. Okay, so we did some benchmarking both on the estimation side, pose estimation side, and on the pose tracking side. So for pose estimation, we used the very popular YCV video data set. It has a fairly decent number of object classes, some with symmetries, and also it's widely used for it's a good representative data set for indoor like manipulation type applications of robots. So what we see here is that our method is not the best performing method. So there are some like recent state-of-the-art models which do somewhat better, not a whole lot, but definitely slightly better. But we are like competitive across the board, regardless of the object type. When we go to post tracking, we actually outperform the state of the art methods. So which shows that the fact that we used these color pair as sort of an unifying descriptors to generate our features, that definitely has some merit. And what I'm particularly excited from, again, a long-term robot autonomy and deployment standpoint with low-cost commodity hardware, sensors, and everything, is that there will always be these noise and like missing frames and all. So as I told you, we ran some tests by deliberately not showing all the frames or feeding all the frames to the robot. So in fact, we skipped like 4 frames at a time, and then it gave like the robot every fifth frame, and then asked it to track the poses of the objects, and it did remarkably well. It wasn't as good if it had seen all the frames, but still, if you look at this average performance, that's better than all the bench methods that we benchmarked against. We did some ablations study to sort of identify what is actually helping the overall framework do well. And we see that kind of like as we had conjectured, that the use of these color pair filters is like avoiding a lot of these kind of crippling errors which can happen either on your 3D translation estimation side or on the rotation side, which helps a lot when again you have these missing frames or some like noisy observations. So these kind of critical errors are what are being tackled well by our use of these color pair filters. And then last but not the least, we are very happy with the runtime performance. So everything is working on a standard Jetson AGX Orin platform. So for initial pose estimation, it's about 7 frames per second. We set out with the target that we need to exceed 5. So we do that for 5 object scenes. So now there can be more cluttered scenes. So there is still scope for improvement there, but at least on YCB type scenes, it works well. And then once the estimation is done, the post tracking is actually even faster because it can reuse a lot of the information, temporal coherence and all from the previous frames. So it is definitely like deployable on like commodity robot platforms. So that was the main target that we had initially. So here is like a quick demo of it working on a Locobot, which is a very low cost robot platform. You can see that there are some jitters, but it's fairly like stable in terms of the estimating and tracking the poses of these objects. Hey. Okay, so to sort of summarize, we presented this unified framework, and for texture, again, it's only going to work for textured objects to do both pose estimation and tracking. It does not require, that's again to reiterate, does not require any pose label training, and it works in real time with full onboard processing. And of course, this is kind of our first step in like real-time robot pose estimate, object pose estimation and tracking. Lots of scope for future work. There will be objects that the robot will be dealing with which will not satisfy our like criteria, textureless objects, reflective objects, and other challenging cases. So we need to augment our framework to deal with those scenarios. And one of the ideas that we are working on actively right now is to bring these topology inspired work that we have shown works well for object recognition, detection recognition, to also combine that with these color pair based post tracking work. Uh, and the other, I think, the big direction that we are looking into is what happens when the robot encounters novel objects in more open world perception scenarios. So can we like also have a version like if it does know about the objects or has like the CAD files or meshes, great, it can use it. But there will be other new objects for which those information will not be there. So then like what can the robot do? Can it like rely on some maybe query a VLM model to find some information? Maybe it can also work with like a human and get some like user responses to get some ideas on what those objects are, and then blend it with more of these sort of like structure based formulations. So we are looking actively into those directions for the future. So thank you once again for staying with me. Questions are welcome, and feel free to reach out to me, and we have the code and everything available for use as well. Thank you again.